places to sit. So, all right. First of all, good evening. My name is Brian Weiner. I'm the chair of the physics department here at Ohio State University. And on behalf of the department and the College of Arts and Sciences and the university, I want to welcome you to the 56th annual Alphaeus Smith Lecture. Just a little bit of information about this lecture. It's held annually, and it is intended to bring distinguished scientists, such as our speaker tonight, to campus to share their insights about interesting scientific results in the past few years. And so you're going to hear about that. The lecture itself is a tribute to the memory of Alphaeus Smith. And just to give you a little bit of background about him, he came to this university as a physics professor in 1909. He was in the department and became department chair in 1927. Let's see, it was 1938, he became dean of the graduate school. And then he retired in 1946, but he actually didn't leave the university. They actually corralled him back, and he became president of the Ohio State University Research Foundation. And he was president of that foundation until 1958. And he oversaw a tremendous growth in research at this university. So I think it's appropriate that this lecture, which is named for him, is talking about current research. So if you do the math, he served the university for almost 50 years. And so this lecture is a tribute to that service. And the first one was held in 1960. Today, we are privileged to welcome Professor Rainer Weiss as the Smith Lecturer. He's an emeritus professor at the Massachusetts Institute of Technology. This is a place where he spent the vast majority of his academic career. He got his bachelor's at MIT, he got his PhD at MIT, and after a couple years at, I think, Princeton as a postdoc, he returned and became a faculty member at MIT in, I believe it was 1962, 64. I think I got that right. And he has been at MIT ever since. So, quite a while. That's quite a career. He's had a role in many different experiments over the years. You're going to hear about one of them tonight, but another one had to do with the cosmic microwave background that he was involved with. And for his efforts, he's actually been recognized with many different honors, and I'm just going to list a few of those. He is a fellow of the American Physical Society. He's a fellow of the American Academy of the Arts and Sciences. He's a member of the National Academy of Sciences. And he is a recipient of the Einstein Prize from the American Physical Society, the Kavli Prize in Astrophysics, and oh, by the way, last year he shared the Nobel Prize in Physics. And so those are just a few of his honors, and yeah. So tonight he's going to speak to us about exploration of the universe with gravity waves. So once again, let us welcome Professor Weiss.
Got the other one? Okay, good. Hey, don't go away. Thank you. Thank you very much. Wow, what a hell of a reception this is. I'm glad to be here. This has been a very interesting pair of days for me. I've never been here before. I mean, when I was a kid, I knew of a radio astronomer who was at Ohio State University named Krauss, and I've read his books. He was wonderful. And now they tell me that he was way before many of you others were here. But the thing I learned most from is most of your students are fascinating, and your faculty is delightful. So I think you're very lucky to be here. I have to tell you that. I enjoyed my stay, and I've learned a lot. So it's a pleasure to come here, and I'm also very glad you invited me to come, because I would have missed many of the people I talked with if that invitation hadn't been tendered. So I will talk to you about what's on the screen here. And I want to say something before I start with that, and that is that this project you're going to hear about is a project that was supported by the National Science Foundation. And in the process of doing that, they took an enormous gamble, and you'll see what the gamble was. And they took that gamble in a way that was really quite remarkable. It was a thing where you'll find the technology had to be developed to do this, and then at the time, even when the technology was developed, we weren't sure what we might see. We wouldn't, here is the thing, we were asking the people to give us $100 million, maybe even $200 million for eventually. And we couldn't really tell them that we could do it, for sure. And we didn't know exactly what we could tell them we would discover. So that's pretty impressive in terms of the following idea, namely that there always should be a little bit of money in this country going into science that is sort of iffy and risky. You don't want to do only things that you're absolutely sure of. Sometimes you win, and this case they won. We all won, not just they, me, all of us, you as well. And then sometimes you lose, but you have to take the gamble. So let me start by starting you into this business with not everybody here knows general relativity, not everybody knows the intricacies of all of this. So I'm going to try to bring you along, but there are going to be a few slides which are for experts. I'm sorry for that. I'll keep looking for you. If you fall asleep, I'll go a little faster, okay? But the thing is that you're going to have to live with some things that are quite primitive and that are understood by more people. So the gravity that most of us learn in high school and in grade school, and not grade school, but certainly high school and college, is the gravity of Isaac Newton. And this is embodied in this equation right here. What it says is that, and this comes from, it's an apocryphal story, but it comes from something which was very deep. It comes from Newton, certainly knowing all the stuff that happened before, Kepler and all the things that were done, but noticing that things that fell on the earth, like an apple maybe, in his backyard, did the same kind of motion as the moon did if you looked at it over a few days. The moon was falling, it looked to you as the moon was falling to the ground. And that association of that gravity had something to do with the evil spirits that were on the ground and the heavenly angels, making that association, was a very big step in the history of science. That's why it's called universal gravitation. It's a very simple law. It's a law which says there is a force between masses, things at mass 1, that's one person, or that's another mass, and that force gets smaller the bigger the distance is between them by the square of the distance. That simple 1 over r squared, or 1 over distance squared law explained most of the solar system. It had a little problem with the planet Mercury, but that's a tiny little wart on the thing. It wasn't really very important. It's good enough for doing almost everything that you did. The space program, our space program, and the Russian space program didn't need to know more than this. That did it. But there's certain things now that you can't do with this. For example, all of you have cell phones. That won't work for the cell phones in detail. If you actually, when we get to it in a minute, you'll see that you have to modify this theory so that instead of going to your neighbor's house, you go to your house. Okay? So anyway, so this law then was a very powerful law, but it was replaced by Albert Einstein in a very much more complicated but more overpowering law. Now, this is a little bit of an anachronism. Here's Albert, a little too old. He did this when he was a young man. And here is a picture of an old man. I'm sorry for that. This picture should be changed. But what is this equation? This is that equation which is actually a substitute for an enormous group of equations. Gigantic, goes on for pages and pages. Anybody who I bet he was working on with this equation knows that this is just a very shorthand way of writing it. But what does it say? What this equation says is that the geometry of space and time, the way you measure space, the way you measure time, is affected by the distribution of matter and energy. That's what this is. This 2/8 pi is just a number, but this is the important thing. Matter, the geometry of space-time is affected by the way matter is distributed in space. And I want to show you a picture. I can't explain the equation to you, except by this sort of homely little picture, which I will try to explain a little better. What this picture is, how many of you know what a jungle gym is? Just raise your hand. Yeah, a good number of you. So not only New Yorkers know what a jungle gym is, but some of you guys out here know what a jungle gym is. It's a big framework that kids play in, and you have bars that go in the X direction, bars that go in the Y direction, bars that go in the Z direction. They meet at all sorts of places in between. That's what you have to imagine when you look at this picture. And what you have done is you've taken a cut in the middle of the jungle gym, a two-dimensional cut. Just cut the thing, and you're looking at one slice of the jungle gym. So you can see here's the jungle gym. And these are all the coordinates in the jungle gym. And now what's been done, these look nicely square and they're nicely separated with even spacing. But here you plunk into this thing the sun, which is a thing that has both mass and energy. And then you plunk the Earth into it, which also has a little bit of mass and energy. And what they do is they distort the geometry. The geometry is distorted by the mass and energy of the sun. And straight lines are no longer straight lines, they are curvy lines. And the other thing which is not in this picture is that, and this is a little hard to draw, but you have to listen to it, is that wherever you have placed a clock, suppose you place clocks at every intersection point, here, 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 everywhere where there are bars that intersect, you place a clock. And what you do out here, very far away from these objects that have distorted the space, all the clocks keep the same time at the same moment of time. They all read the same time. You may not be able to prove that with a camera because it takes time for the light to go into the camera and you get different times on the clock. But if you go to them with your own little clock and measure them, you'll find out they all read exactly the same time at the same moment of time. But the clocks that are in here where the space has been curved, they run at a slower rate than the clocks out here where there has been no change of the geometry. So time gets affected as well. And that's a very important effect. So two things get changed. Space gets curved and time gets warped in a way. And now there's a very famous statement how this makes an explanation of gravity. Because now what happens, and this was Einstein's lovely interpretation of this, later interpreted by John Wheeler, the objects that are in there, the sun and the earth, in this case the earth mostly, moves along those paths that are the shortest in time and space. They don't get forces on them. There are no forces anymore. Gravity forces are gone. But the geometry of space-time tells things how to move. And that's the way you want to think about this new idea that Einstein had. It's a brilliant idea, and it predicted some things, and one of them it predicted was something that Newton couldn't have done, was that there is information transmitted in a gravitational field, a structure like this, which does take time to go from one place to another. In other words, in Newton's theory, if you want to ask how long would it take for information, let's say like somebody plucked the sun away, how long would it take to stop seeing the sun? Well, we know the answer to that. It takes about 9 minutes if you did that, 9 minutes in times of the light. It takes you 9 minutes before you know that somebody has taken away the sun. How long would it take, in Newton's theory, for the gravity of the sun to be no longer affecting the Earth? It would be instantaneous, but that's not true. It can't be that way because Einstein told us the fastest that information can travel is at the velocity of light. So that, you would not know this for 9 minutes also, that the sun had been plucked away. We'd be going around our orbit, the sun has suddenly been removed, and we would then go off on a tangent in our orbit, no longer being attracted to the sun. So, that phenomena, that is the information transfer in gravity, is called a gravitational wave. Okay? So now let me show you a gravitational wave. Einstein wrote 2 papers in 1916, one, and another one in 1918, in describing this. He made a mistake in one, but it's not important. There are 2 papers. If you want to get the full treatment of Einstein doing it right, you've got to go to the 1918 paper. But he already knew at that time, when he wrote those papers, that gravitational waves are generated by accelerating mass. That's very much like in electricity and magnetism. Electromagnetic waves are generated by accelerating charges. But here they're made by accelerating mass, but not all motions make a gravitational wave. It has to be non-spherically symmetric motions. Motions like 2 things smashing into each other like that, or 2 objects going around like that. Things that blow up like a balloon and then contract again like a balloon, they do not radiate gravitational waves. Einstein thought that in 1916, but then he reversed himself in 1918. So, okay, those are the sources of the waves, and here is the properties of the waves. And the reason I want to make a fuss about this, this allows you to understand how we detected them. So first of all, we now know for a fact that gravitational waves propagate at the speed of light. That was assumed by Einstein. We know this now, and you'll see later on in the lecture how we know that. But he assumed it. And the other thing is it's a transverse wave. Let me explain what a transverse wave is. A wave that's transverse, and that'll be coming out of the picture on the front. You know, that screen will have a gravitational wave coming at you in a minute. And it does all its dirty work not in the direction in which it's moving. It does things perpendicular to the direction in which it's moving. And let me show you what it does. Yeah, you'll get a little dizzy if you look at this too hard, but keep looking enough. Right here where there's a red square, I hope you can see this square, right there is you. You're standing there. And these dots are little sprinklings of masses I put into space all around. And Now the gravitational wave is coming out of the screen, and look what it's doing. If you look at it a little bit, you'll notice that it's contracting space in, let's say, one dimension, while it's expanding space in the other, and that keeps flipping back and forth. Can you see that? X in one dimension, it's contracting space, and the other dimension, it's expanding it. And it keeps flipping back and forth from which one is being contracted, which one is being expanded. So that's the actual motion that a gravitational wave makes in space. That gives you the first sort of imagining how you might go after detecting one of these things. And then there's another property, which is, if you look at that, this is a little more subtle, but not impossible to understand. If here you are again, look at the two objects that are close to you. They're not moving very much. But the guys that are very far away from you, like there and there, they're moving a lot. So there's a ratio in that picture that is the same all along a line. It's that the ratio of the amount of displacement, the amount of motion, is proportional to the separation of the objects to begin with. It's very much like you and a friend taking a rubber band. You can't do this because your hand, you have to hold the rubber band in your hand. Get your friend to make marks on the rubber band every eighth of an inch or every quarter of an inch, and then pull the rubber band. It's exactly the same kind of motion. And what's that called? It has a fancy word. We'll see that word in a minute. It's called the strain. The property of the gravitational wave that is the property all along a line is it has a strain. It makes a strain in space, which is the ratio of a change in position divided by the change in position of two objects divided by their separation. Now we'll run into this more and more. Okay, so there it is. That's a gravitational wave, and I want you, we'll exploit your understanding of a gravitational wave in a few minutes. But now I want to talk a little bit about the history of the discovery of gravitational waves. It was not discovered by LIGO. I know people say that, but it's not true. It was discovered by these two people. Russell Hultz was a graduate student at the University of Massachusetts at the time when Joe Taylor was a professor there in the physics department, but he was doing radio astronomy, and Mr. Krauss, Professor Krauss, was a guy who certainly trained these guys in doing the radio astronomy. And what they discovered was a very interesting system. What they discovered, and the person who discovered it was Hultz. The graduate student discovered this. He was out there at Arecibo, which is a great big dish. That's in Puerto Rico. And they were listening with headphones to the receipt of radio signals from the distant. And they ran across an object that was going brrrr like that, 14 times a second. And it turns out, or 17 times a second, sorry. And what they then modeled what it was a star that was called a pulsar. That's a star that has the mass of the sun, but is no bigger than Columbus, Ohio. The diameter of the thing is no bigger than, maybe it's even a little smaller than Columbus, Ohio. So it's a crazy star. It's a star that's enormously dense. Imagine, and it has, if you had a spoon and tried to figure out, grab a piece of the star, you couldn't lift the spoon. It has a density 10 to the 15 grams. And I'll get to powers of 10 in a minute. Huge density. So it turns out there is one of these pulsars. It has a little beacon on it and makes these pulses, and you pick them up in the radio dish. And so they imagine the radio dish right here. And so the second thing they discovered, they heard this thing making that noise, but they noticed something very interesting. And this is the model they made of what they heard. Every time, and this is what they found out, it was a star that was around another star they couldn't see. This one wasn't making bursts. And what they found is that this star they're going around each other, and the one that was making the noise would go a little faster when it was coming toward the detector. And then when it was going away from the detectors, the dish, and it was going a little more slowly when it was going away from the dish. Very much like what happens to you when you get caught on the highway from a cop. You know, he's behind you, and as he's coming toward you, you're just speeding, and you hear him, and as he's coming toward you, he's making a high-pitched sound, but he's not looking at you, he's looking at the guy in front of you, and so when he passes you, the pitch goes down. Okay? That's called the Doppler effect. Okay? And so what happened is they found this incredible system of a star that was a very little nugget of a star, and apparently it seemed to have another nugget that was going around it, and it was going around and around. It was a perfectly wonderful laboratory for doing general relativity, for testing Einstein's ideas. And the picture I have over here was the discovery of gravitational waves. What is this picture? This picture is, on the x-axis, is epic. For example, here's 1973, sort of the time when they began measuring this system. and here is 2000. And plotted along this axis is the time it takes for these two guys to go around once. How long does it take them to go around in the orbit? And it's getting shorter and shorter. That's what this is. These are negative signs here. You won't see them, but I can tell you. And what this plot, these dots, all the little dots that are in here, are characteristic of the time that they measure. It's a very straightforward experiment to measure. And they notice the time is getting shorter and shorter. Now, what that means is these guys are losing energy. That sounds a little persnickety, doesn't it? Things that's going faster is losing energy. You'll have to abide with that for a while, okay? But that's what's happening here. And so what they did is they plotted, these are the dots, and they went to the Einstein equations and said, what happens if you have two objects going around each other and they are radiating gravitational waves, and that line that goes through all those dots was the result they got. So they were the first to see gravitational waves. They saw the loss of energy by these two stars, two gravitational waves, as they were orbiting around each other. That was a big, big discovery. They won the Nobel Prize, not only for this, but all the other kinds of measurements you can make in this very elegant system in 1993, I believe. If I'm wrong, correct me, okay? So that's the discovery of gravitational waves. Now, here it was a person at the University of Maryland, this is more of the history, who actually began to think that he could detect gravitational waves. And that idea was sort of becoming an emerging idea back in the early 60s, or maybe the late 50s of the last century. 1957, it sort of began. And this is Joe Weber, who was both a physicist and an electrical engineer, and actually a very good physicist. Interesting, imaginative person. And here he is working on his idea. There he is. And what this idea that he had was, here's a great big piece of aluminum. You can see it's quite big. It's bigger than he is. And he's mounting little strain gauges on it, little things that measure the distortion of that piece of aluminum. And he's mounting them, and he wants to do the following. He's hoping that a gravitational wave will come along and do the trick I showed you in the picture. Stretch space, and then stretch one dimension of that bar and shrink the other, and then flip around and do it, and set that bar singing like though it had been hit by a hammer, very much like a xylophone. And that was his whole idea. The gravitational wave comes along, bops this thing, and he would then listen to it after, then he set up a whole experiment. One of them at Argonne Lab, where you were, and another one in Maryland, and then another one at a golf course not too far from the University of Maryland. And to his misfortune, he saw typically 3 pulses a day in all 3 of those detectors. And he saw that they were coincident. They were at the same time, or at least as best as he could tell. And he made a very bold and probably not very wise decision that this was the detection of gravitational waves from someplace in the center of our galaxy. Something was making gravitational waves, and his best explanation for why those 3 bars were being excited simultaneously was it was gravitational waves. And why do I say it was a misfortune? Because it started the field in a very complex way. It turned out when you discover something like that, which is very profound and very important, I mean, another very important piece of evidence for Einstein's theory. And this is not such a complicated thing to do, to mount some strain gauges on a big piece of aluminum. It's not even that expensive. So a lot of people in the world were able to do exactly that same experiment. And it turned out, he published the paper of his discovery in 1969, and by 1972, it was quite obvious to very many people who had tried the experiment themselves that there was nothing to it. There were no gravitational waves, and that caused a great deal of trouble for everybody that followed. Okay, because it looked like it was a pathological science. There was all sorts of internal fighting within the physics community, whether he had done the experiment right. I don't know what he was seeing. I'll be honest with you. I have a theory. You can ask me that in the questions later, but I have never been able to confirm it. So that was the beginning of the field that later did do something, make a discovery. But that was a bad beginning. Look, don't get me wrong. I have a tremendous admiration for Joe Weber. I mean, he is a guy who had the idea. He had a very good idea. It's his implementation of the experiment. I think he was too eager to be right. People tend to do that when you get really immersed in something, it's very good to have somebody else working with you, okay, who keeps you honest, because you can delude yourself. And I think that's what happened. That's my guess. Okay, so now here is the thing that actually made the detection. I'm going to go slowly here because I want you to understand this. The idea was that, and this occurred to several people, about how another way of making the detection would work. And the idea here was to actually do what that picture of the dots shows. Namely, but you do it with light and the timing of light. That was the idea. So, for example, in that picture I showed you, this is going to be a laser in this animation you're going to see in a minute. And this is a beam splitter. This is a device that does the following. You send light at it, and half of it gets reflected, goes down to here. Half of it gets transmitted and goes to there. Okay? So this is called a beam splitter. And by the way, you experience this every day. When you go look in a shop window and you see your reflection in the window, and you also can look into the shop. It's not a very fancy thing. Beam splitters exist everywhere. And so the idea was that, when this was the idea of this thing, is a gravitational wave comes down on this thing, and what it'll do is it changes the position of that mirror, pushes it out, let's say, and pulls this one in, and now it'll destroy something, which we'll talk about in a second. But now, here, let me get it started so I can show you what really is going to happen. Okay, so wherever there's red, that means there's light power, and the wiggly thing in here is the electric field in the light. Remember, light is a wave phenomena. It's just hit that mirror. These paths, this path and that path, have exactly equal time for the light, and so what happens is no light goes to this detector. The two waves cancel each other. And that's the situation if there's equal time spent in these two arms. Now comes a gravitational wave, pushing on this, pulling on that guy. And you'll notice when their path lengths are no longer equal, there is light, there is red, and these waves don't cancel each other anymore. That's all there is to the detection of gravitational waves by LIGO, by the way. How many of you are now totally confused? A few. Can you, well, I don't know. I best ask you, not enough of you, so I'm not going to stop. You're going to have to live with your neighbor telling you, okay? There's only a few of you. But let me say it in English. What is being done here is you set a trap for the gravitational wave, which is the following. You make a device that lets light in, you measure the time it takes light to go back and forth from that beam splitter, and then you take the light and recombine it, and the light will not go to the photodetector if the time that the path took is exactly the same in both directions. Exactly the same. Has to be exactly the same. But then the gravitational wave comes along and disturbs it. It makes one path a little longer and the other one a little shorter, and then no longer you get this perfect cancellation. And that's really what the basis of the whole idea is. Okay. Well, then along comes Kip Thorne, who I know talked here about interstellar. I was told this over and over again. And Kip is a good buddy of mine. Well, Kip sort of threw a cold damper on this whole thing because he told us, and because he knew a lot more about astrophysics and gravity than I did or others, and that was his business, as he's a theorist. But Kip was a quite young man in here. He didn't look that way when he was here, I guarantee it. He was a dapper character. I mean, look at this lovely tie he has. Anyway, it's a little more formula, and now I have to really come down and bite the bullet on what powers of 10 are, okay? I know for some of you this is new. So what Kip said, if you're going to try to measure gravitational waves from an astrophysical source, you're going to have to do a hell of a lot better than Weber did. That's something we knew. Weber couldn't have detected anything. He was 5 orders of magnitude away in being able to make even the slightest detection. So Kip said, look, if you want to get into business with any technique, you're going to have to measure strain, H. That's a symbol for strain. And this is that ratio, which is the change in length between the change in position of two objects that is separated by a distance L. That quantity has to be, it won't be very much bigger than 10 to the minus 21. Now, what does that mean? How many of you, I just want to know, just for myself, how many of you are familiar with this powers of 10 business? Not everybody. That's very interesting. Okay, let me give you a half a minute on that. That's very important. There is no English word for 10 to the minus 21. It means, for those of you who like decimals, it's a decimal point, 20 zeros, 0.0000, 20 times, then a 1. Or it's the same thing as having a fraction, which has a numerator of 1, and you have 10 times 10 times 10 times 10, 21 times in the denominator. It's a nice, compact way of writing very small numbers. That's always a negative exponent. It's a lovely way of writing very big numbers. So, for example, our budget, the budget of the United States is $1 trillion. That's 10 to the 12. Most of you don't know that, or some of you do. But it's much easier to remember. It's not $1 billion. $1 billion is 10 to the 9. Okay? So I wish the newspapers would start using this technique. You could understand what the hell's being done. And you would know a tax break wasn't a good idea. No. Okay. All right. I'll leave it go. All right. I'll get sued for that, I know. Okay, so that's the best I can do. You write 100. 100 is 10 to the 2. 100 times 10 times 10. That's 100, right? 10 to the 2 times 2. Okay, so we have this very small number. And if you now have 4-kilometer lengths between the arms of this device that is going to be built, that is LIGO, in fact, you wind up with a change in position over 4 kilometers of only 10 to the minus 18 meters. What does that mean? Well, it's tiny. An atom is about 10 to the minus 11 meters. And you can just about do an experiment in your bathtub to see how thick an atom is. I won't go into that. Ask me that if you're interested. Okay? It's a very pretty little experiment as a science experiment, using an eyedropper and dropping something into the bathtub water. But on the other hand, 10 to the minus 18 is even smaller than an atom by a huge amount. 10 to the 7 times smaller, 10 million times smaller. And so consequently, this is a measurement that you have to perform, which is really quite difficult. And that's why it became such a challenge. And one way to say it very well is these two statements here. One way of saying what 10 to the minus 18 is, and this is more for experts, but it's one way of displaying what the problem is. It says that you're going to have to make a measurement of the endpoint of those mirrors, which is 10 to the minus 12, or a million times smaller than the wavelength of light. And the wavelength of light is very small. It's about 10 to the minus 6 meters. That was hard, but it wasn't as hard as the next one. You're going to have to make also sure that you can somehow place those mirrors in such a way that the vibrations of the Earth and all the things that are wiggling don't fool you, that allow you to look at these tiny excursions made by the gravitational wave. And there is another factor of 10 to the minus 12. You and I are all wiggling here. We're pretty far from the ocean here, so the number I'm about to use is about right. You're wiggling up and down in this hole by about 10 to the minus 6 meters. You don't know it, and you don't feel sick about it. But that's what you're doing just due to the seismic activity of what's going on in the world all the time. And what's that due to? It's the winds and the ocean waves are doing that. And they propagate all the way across the continent. So, okay, those were the two challenges. And now, here is the way, what the hell else? Did I lose a slide here? No, I didn't. Okay. Here's what, I just want to show you some of the tricks, that's all. Some of the tricks that were used to get that very big factor of improvement in position. So this is what the interferometer actually looked like. And what is it? Let me walk you through that a little bit. What you already know about is the laser. That was in that animation, and that beam splitter, and you know about this mirror, and you knew about that mirror. There's 3 other mirrors in here which I haven't told you anything about. This guy, and that guy. And there's a detector. So what you put a mirror in here, that is not a complete mirror. It's a little, almost a mirror, but it lets a little bit of light through. And what that does is it makes the light bounce back and forth about 300 times. So what that does is it makes the gravitational wave interact with the light a lot longer or for a longer distance. That's one trick that you have to do to get that big factor. That's also happening in this arm. So that's one way of making it. And what that does is that you make, again, that these are identical to each other. Make the time that light spends doing that in here the same as the light is spending in, and then you get no light to the photodetector at all. So where does the light go? Well, this is an invention that both the German group and Ron Drever had. The idea is it goes back to the laser. That's where it's going. And all the light that's put in by the laser, if there's no light going to the photodetector, it does all this stuff. It doesn't get lost in the mirrors. It all comes back to the laser. And lasers don't like all their light being put back into them. They hate it. And so what happens is what was done is you put another partial mirror in here. And this does a very clever thing. What it does is it takes the laser light and reflects it. You don't see this in the picture, but you have to follow what I'm saying. You hit the mirror and reflect. But then remember, the light comes back out of this thing, is going through the mirror, is heading back to the laser. So you have two beams, one the reflected beam going back to the laser, another one going to the laser from the beam splitter. And those two beams, you can make them cancel interferometrically. Make them cancel just like they do to the detector. And that then makes it that all the light out of the laser, none goes back to the laser. All of it winds up in this system. And for example, if you start with maybe 10 watts of light here, you might have 500 watts of light in here, and you might have something like 200 kilowatts of light in here. So you've built up the light enormously. And these are all the little optics tricks that you have to pull to get that sensitivity. I want to dwell on this only a little bit, and I'm not going to explain it. This is now for the experts a little. Okay, one slide for the experts, and one other one. What this slide is, and you can follow me, I hope, a little. What this is, the strain spectrum. This is how much strain there is at each frequency. And this is the frequency. So this is a plot of the noises that were in the very first detector we made, the LIGO detector we made. And you can see the envelope of the things that made the noise. At high frequencies, we didn't have enough light. And if you had more light, this would come down. At middle frequencies, right in here, the thing that dominated was the fact that all those objects that were the mirrors and everything was at room temperature. And room temperature is suffering Brownian motion, it's called. Those of you who play with biology probably know all about that. You find little particles that, if you look at them in a microscope, they're always jiggling around because they're being kicked around by the motions of the liquid, because the liquid is at room temperature. If you freeze everything stops when you freeze everything. So it turns out this is just the thermal motions that are induced because you're operating at room temperature. And this thing, that's the other limit here, and here's 100 hertz, so you can see where this initial detector was. This is the seismic noise, the noise on the Earth, already as well filtered as we could in the initial detector. So that is the envelope, and these are the noises that you had to fight with. And I want to point two other things out in this picture. And this is now for people who want to look forward to where this field might ultimately go. The noise that is this noise right here, which determines how well you can determine the position of the mirror with light, is followed by something which was not a problem in the initial detector, but is called radiation pressure noise. And those of you who have studied little quantum theory know that if you try to measure the position of something with light, the light pushes the thing that it's measuring around. It has momentum. And that is the effect. This line is the effect of the quantum theory of light. So that's something that's going to be with us forever. The other one is something here which I do want to explain to you, which is the reason why later at the end of the talk we're going to talk about that you have to go into space to make measurements of gravitational waves at very low frequency. For example, this is 10 cycles per second, and here is this noise that's called gravity gradient noise. What is that? You can do very well, and we'll see a system in a minute, that takes out the ground vibration, the accelerations from the ground. You can do that. Why? You can make a measurement relative to the fixed stars. All the stars in the universe give you a reference frame, and if you can make yourself stationary with respect to them, you will not be accelerated by motions of the ground. And that's a trick we use over and over again. We'll show you one in a minute. But the other one is that you can't do the following. When a seismic wave, seismic compression wave comes along, which moves on the surface of the Earth and it compresses the ground. Okay, here's the mirror, let's say. Well, that mirror then is pulled over to the ground a little more when the ground is compressed. It's denser there. So this mirror gets sucked over to the compression, and then it expands, and then it relaxes. So that's an interaction that's between the density changes in the waves interacting with the mirror by Newton's law, the law that we started with. And so that you can't get rid of. You can't shield it. You can't do a damn thing about it. You really can't do much about it. So one thing you could do, you could try to measure the densities, and people are trying to do that. So that is this noise, which is, and the atmosphere does the same thing, the density fluctuations in the atmosphere. So you can see this is a fantastically fast curve. It goes up by many, many, many orders of magnitude in just a few cycles. So that's a very hard noise to deal with. And that's the reason we have to go into space. Okay? I won't tell you about the other curves there, but I had to do that for those people who want to know where this field is heading. Okay, so now, this is now what the situation is of gravitational wave detectors. There are two in the United States, one in Hanford, Washington, another one in Livingston, Louisiana. Those are the LIGO detectors. There's a detector in Italy called Virgo. It's near Pisa. There's a detector which is only 600 meters long. It's mostly a research detector. It develops a lot of the interesting technologies. And there are two detectors that are under development. One is in Japan. It's called the Kagura Detector. That's being built in the Kamioka mine where the neutrino detectors are. And another one is called LIGO India, which is just getting started. And these things will be ready sort of, Kagura hopes to be ready in about the end of the, well, in 2019 they hope, but I think it'll be later than that. And LIGO India will probably only begin really operating by 2025. And why do we want all those detectors? Why does the world want all those detectors? It has to do with what we're about to talk about when you make a discovery. First, let me show you what LIGO looks like. This is a little travel log of LIGO. You're looking down on the LIGO, and this is the situation in Louisiana. There are trees there. And you can see the beam tubes. Here's the thing in Livingston. Here's the thing in Hanford. And these are concrete covers over the vacuum system. And this is now the same thing in Louisiana. There's trees. And so this is what the tube looks like. The laser beams go in this vacuum, very, very high vacuum. And here's a laser table like you have in the next building over. I've seen a couple of those. And this is the control room in Livingston, and people are in there learning how to operate the machine. And that's sort of it's pretty big science. It's reasonably big science, okay? So, okay. So, I want to avoid this picture. I just want to tell you what it tells you. Well, maybe I will tell you, because I hope you have a little patience with me. I will keep looking at you. But the thing is, what is this? This is the progression of the sensitivity as a function of time. All these curves are different times in the history of the initial LIGO detector. We started up here as a function of frequency, and this is sensitivity. Well, we did very badly, but little by little, over about 8 years, we got down to this. And then and you can see there's this curve in here. That's this curve that we should have made. We almost made it for most of the band of LIGO. So we call that achieving the design sensitivity. And because we did that and we did not see anything, we saw a clean zero. Most people say, that's crazy. What's a clean zero? Well, we saw what we saw we could explain, and we did not see any gravitational waves above the noise. We were sure of that. So we could tell people, we did our best, the thing worked as well as it could, but we didn't see anything. So please give us some more money to build something better. Okay? Well, that's what was done. And that was part of the plan. And I won't describe this to you any more than just to show you that the changes that were made that actually made it that it did make a detection all had to do with that other thing that Kip told us we had to do. We had to improve this isolation from the ground noise. And so this is, for example, these are modifications that were made later in the second issue of the advanced LIGO detector. What this is, here's the mirror that does the reflecting, but it's supported from another mass, and that's supported from another mass, supported from another. What that is a whole set of masses, and here's where the ground is connected with springs. And so this is the idea. This is that you can do this experiment at home for yourself. In fact, those of you who've taken a course, freshman physics course, can do it right away. To have a string and mount something like a cup on the bottom of a string. And here's the ground, and here's the cup. And what happens if you move them slowly together, they move together. There's a string between these two. But if this guy moves fast, this one doesn't move at all. And that's the kind of filter that you need to get rid of the ground noise. You can play that game at home if you want to try it. It's not hard. Okay? I could take my belt off and then my pants would fall down. But you don't want me to do that. So the other thing is, this is done 4 times. That helps enormously. And in here, I won't describe it to you any more than what that is how many of you ever have used these headphones that stop the noise coming in from the outside? You know, the Bose headphones, a lot of people who fly a lot use them. And these are things where you do something very clever. And what's done here is exactly the same idea. You take and measure the amplitude of the noise coming in from the outside, the engines or whatever it is, and then you feed that back into the headphones, inverting it so that it cancels what got through the headphones. And that's the same idea here. What happens, and this is a very important idea that maybe some of you who have labs here would like to have, you have seismometers which measure the motion of the ground, and they are mounted on things which push on a platform. And what you do is you push on the platform so the seismometers get nulled. They do not have a signal anymore. And that's the same idea. And that was very, very important in LIGO. So here then is what was discovered. As soon as we did this, within a couple of weeks after we had all of that running, we saw this. What did we see? Well, we saw a signal, and this is a signal at Livingston, this is a signal at Hanford, and this is junk. By the way, what is this? This is time. So here, for example, this is 1/10 of a second. From here to there is 1/10 of a second. And look at the units on the vertical axis. This is 10 to the minus 21 strain, just about what Kip figured. And this is junk. That's nothing, but a little something starts forming out of the junk. And you can see this oscillation, which is getting bigger and bigger and bigger, and then it stops, and this is junk again. So this is the same thing that happens at Hanford, but not at exactly the same time. About 7,000ths of a second later. That tells you something. That tells you that whatever this was hit Louisiana first, and it took 7,000ths of a second to hit Washington State. And that turns out to be close to the velocity of light for something traveling that distance in such a short time. And what did they see there? Well, they saw junk. It's not the same junk as that junk. That's noise. But this sort of thing that evolved out of that, and then there was junk again. So these two signals, if you slide them relative to each other by 7,000ths of a second, you'll get something that looks like this. And they're on top of each other. But they're not the same. Why? Because there's noise in the system. But this was enough for us to actually start looking at it. And here is a nice way of representing it, another way of representing the signal. This is a representation where you take that series in time and convert it into a frequency. You're allowed to do that. You know, a time series that oscillates has different frequency components, and you can listen to it. And what this is, and you'll listen to it in a second. So instead of representing it as, here's still the time, but you're no longer representing the strain as an amplitude, you're now describing how much at each frequency is in this signal. And there is that signal. The brighter it is, the stronger the signal is at that frequency. So for example, here's the bottom of the piano, about 20 hertz. Here is middle C, about, that's the same in both pictures. And you can see the signals sounded like this. There's a boop. That didn't, so people they did a trick and they changed the frequency a little bit. Okay. It's a chirp. That's what this is. And now what is it? And this was the other very important part of all the development, the technical development that was done in building the detector was very important, but this was just as important. People had learned how to put Einstein's equations, those things he developed in 1915, on a computer and done numerical solutions. You could not do these solutions with the strengths of the gravitational curvatures that were there without, well, people could do approximations to it, but they couldn't do the whole problem. So it was very, very important that numerical solutions existed for Einstein's equation with a model of what we thought this was. And this is a picture of the model. It's, by the way, what you're seeing here, are going to see, is not an artist's rendition. It's the computer output plotted in the same kind of way as I showed you the picture of the jungle gym. So you'll see. Let's get started. On the bottom is the waveform progression. There is, and you get this will unfold. Here are the two black holes. That's what we thought they were. And they have already made these distortions in space. Wherever the colors are, when it gets dark, it's the clocks have stopped. Where it's red, it's slow, but they're black, they stop. And you'll notice these little arrows. These are the arrows of the stresses in that particular space. It's related to the strain. And you can see these guys going around. They're radiating gravitational waves away. That's the stuff that you see up here. And you can see the time that's going on. Eventually, I'll slow this down, and you'll see a real storm in space-time. It's really unbelievable what you're about to see. There it is. These two black holes are getting close enough, and they're making curvatures that are unbelievable. And the clocks have stopped in there. And now they're about to collide and make a new black hole. And that's it. And there's a storm in space. It's just really quite amazing. And so then the stuff goes off, and that's the gravitation. It's over. That was it. And what we saw was that. Well, that was a big deal. And, well, we didn't believe it right away. And let me tell you, I wound up, after we began to believe it, I went to New York, and I was going to a place to give a lecture to a high school, and I saw this picture in the subway, this one, and I'll read it to you. It says, scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet. I mean, sort of amazing that this discovery, which was sort of had become public in February of 2016, had become now part of the public's imaginings. And so here, this picture was, this is a cartoon in the New Yorker, not about the same time, February 2016. This bird is that bird is talking to that bird. He says, was that you I heard just now, or was it two black holes colliding? Okay, I mean, so to me, it's sort of amazing. And when I went to the talk in the school, they know all about it. And I can't imagine a piece of science known that way by kids. Why? Well, you ask any kid in this country, name a scientist. The first name, if they have read anything, they'll say it's Einstein. You try it. Try it for yourself. Unless your father is a scientist, okay? And the other thing is that they all know what a black hole is. It eats you and it's bad, dangerous. It comes out of the comic books. They're loaded with black holes. I didn't know that. So, all right. So then, we've seen other black holes since then. And that's actually what made it, this is now, the one we've been talking about, this is time again. And here's the black hole that we've just been talking about. That's a black hole, that's the same time series we just talked about, and there's a strain again. And then, these letters, these indicators are a little tricky. This says it's September 14th of 2015. This is October 12th of 2015. We saw something else. That was again a black hole, but a different mass. That's the statistics for these things are over here. Those two holes, they had 36 solar masses and 29 solar masses, and they threw out in gravitational waves 3 solar masses. This one is, I'm not going to read each one of those. This was a combination of 23 solar masses with 13 solar masses, and somewhat longer and higher frequency. Then we saw another one in September. And a very long one, it has very lighter, much lighter masses. And then another one. And we began to believe. It took a while. But that's ultimately the fact that we saw more of them. And I don't want to take time to explain everything in this picture. But then there was a very important event in this business in August of 2017. And that was, here is another black hole. By this time, not that we're bored with black holes, that by no means. But this was sort of becoming, another one, okay? But this one was detected not only by LIGO, I mean, it was detected both in Hanford and Livingston, but also it was detected by Virgo. Their instrument had finally gotten to the point where they could have enough sensitivity and they could see something. And this was a major watershed for Virgo. And what that allowed was something very important, and that's why so many detectors, more detectors are critical. This is a picture of the sky. It's not complete, and this is a picture of the sky. You're looking over the sky, and the uncertainty in the position of this particular black hole pair is huge. It's about 1,000 square degrees on the sky. And you go to an astronomer and tell them, go find this over 1,000 square degrees, they laugh at you. I mean, how can they possibly do a thing like that? They don't laugh at you quite so hard. They still laugh. But when you now take the fact that you also have data that allows you to do timing to Virgo, which is in a different place entirely, and that narrows the thing down to about 30 square degrees. And that's not still barely good enough for an astronomer, but it's at least in shooting distance. And so the fact that you have more detectors and have more timing differences on the world, see, you can't focus, you can't aim these detectors. They take in stuff from all around. They have certain places where they don't detect very well, and that'll become important in a minute. But most on the average, they accept gravitational waves from everywhere. From under the ground, from above the ground, from left, right, everywhere. They don't have much discrimination. And so the only way you can determine where a source is by timing, using the Earth as the thing that makes the timing, makes the differences, positions on the Earth as the timing device. And so this was a very important development. And now comes something which actually was critical, that Virgo was on the air. And this is a different source entirely. This source was also discovered, and then we had this sort of, I call it, magical month of August 2017 was a time when all sorts of things happened. And this is the other thing that was seen, and this is dramatic. What this is now that you're a little bit familiar with these pictures, this is, again, frequency versus time of a chirp. But this chirp lasts for a very long time. There it is. And in fact, at some point here, this thing, which turns out to be two neutron stars, and we'll get to that in a minute, the same kind of objects that Holtz and Taylor saw when they first discovered gravitational waves. It's exactly the same kind of objects. Not the same object. Other ones like it, okay? And what this sounds like is sort of very, very different. Let me play it for you. Why can't I find it? Ah, there it is. Good. Okay? That's a long, drawn-out chirp. Okay? And now, what was so magical about this? What was so magical about it is that what's above, this is the gravitational wave part of the discovery. Here is something that was discovered by a gamma-ray telescope in space, the Fermi telescope. That's a gamma-ray detector. This is a time when we think those two neutron stars collided. We couldn't quite see that. Our detectors don't go to such high frequencies. But the Fermi, about 1.7 seconds later, the Fermi satellite saw what's called a gamma-ray burst. There it is. And then there was another instrument on Fermi also, which was not quite the same sensitivity, and another satellite saw it too. This was the first confirmation of a gravitational wave event by an electromagnetic detection. And if there was ever any doubt that we were detecting gravitational waves, this should stop the doubting, okay? Because somebody else saw it too. And it was quite a dramatic sighting, because what it was here's sort of the same kind of picture that tells you how well you could determine where this thing was on the sky. A LIGO could do it with this little blob and that little blob on the sky. Not very good, still 1,000 square degrees. Now, if you added Virgo to this, you would not, and now it's a very interesting argument with Virgo. They didn't see anything. But they had the sensitivity that they should have seen it. That says that this particular object was in the null of their detector pattern. And that allowed us to say, look, combining Virgo's non-detection with LIGO's detection means it has to be in there. Here is the uncertainty that the Fermi satellite had of where this was. And it was absolutely critical that we had gotten that, because what happened right after that, within 6 hours of this, people with telescopes in Chile who had been looking at a region in the sky, here is that region in the sky, that's a galaxy, and they had taken a picture of it 20 days before the event. Here are stars in our own galaxy, these guys. But this is that galaxy, which is quite distant. It's 140 million light years away. And this is a little bit after, 6 hours after we made our detection. You can see this picture is the same, it has the same stars in it. But lo and behold, there is a new little speck right there where those two arrows are. There was nothing in this picture. Now there is a bright spot there. And now that's an optical observing telescope on the ground in Chile. And that then set off a tremendous investigation by a huge number of optical, infrared, radio, and X-ray astronomers, because they knew where to look, and they found something really quite spectacular. This is the model of what they found, and it keeps changing a little bit every day as you find out more. But the idea was that here are the two neutron stars coming together. They make a new black hole, and the gamma ray comes off not on axis, it comes off a little bit, and this is what the Fermi satellite saw. The LIGO, of course, saw these two guys going around each other, okay? And then here's all this debris that came, and it's called a kilonova. And what does that mean? Well, here's one of the, when you put together what the ground-based telescopes saw, you found a lovely story that was associated with this. And the story is that when you start looking at where the elements that we are made of actually come from. In other words, this was a big, ambitious program that people who did the science of cosmology. And this was Gamow, George Gamow was the first to really start doing this. And I remember as a kid, I read his book, Mr. Tompkins in Wonderland, in which he describes how the big explosion that started the whole universe, which we now are pretty sure of because we can see everything expanding away from everything else, that explosion, in his mind, it had some heat in it, and we know that's true now also. We've measured that heat. And that he then thought that maybe that was the way all the elements were made, in a big oven. That was the universe at the very beginning. And so that idea was rampant, but it had a problem. It was able And this picture shows the periodic table, which many of you have seen in high school or in a chemistry course in college. And what you see is the color coding of where the particular elements come from. So here's hydrogen, and they think it came from the Big Bang itself. That's the initial explosion of the universe. Here's helium, which we also think came from there. And then you look at lithium and some of the other things. It sort of ends there. There's a tiny amount of lithium and beryllium that comes from that initial explosion, but more of it comes from just the explosion of stars, massive stars. And that's color-coded, so you can see up here what the processes are. And that whole process of supernova, which is exploding stars, has populated the rest of the periodic table. And people now believe that, but they had a problem. And the problem, they could populate it up to about iron, which is somewhere in this table. Where's Fe? Somebody can tell me. Up. Where's that? It must be somewhere. It's in this line, isn't it? All right, look. Yeah, you'll find it for me. All right, I can't see it from here. So the thing is that where it's purple, here this is niobium, and these are things which still could be made in supernova or dying stars. But all this purple stuff comes from some process that people thought was going to go on in supernova. It doesn't work. There aren't enough neutrons to do it. And it turns out a couple of astronomers and cosmologists had already guessed that they would be made in the collisions of these two neutron stars. And there has now very strong evidence that that is indeed the case. In other words, we now know, and we have a pretty good idea, that all the very heavy elements, including these things that people love, like iron and, like platinum and gold, come from the debris that falls together in a neutron star collision. And that's been a big science, and there's a lot of papers been written on it, a lot of groups here, people here in Ohio were also part of this whole big discovery process. So that was one of the things that was discovered just from that one big event. There was another thing that was discovered, which is sort of interesting and cute and tells you something about the future. This is a little more abstract, but I'll just tell you what it is, and those of you who are experts will probably maybe already know this. There's another thing you can use these neutron star things for. You can use them as a way of getting what's called the Hubble Constant, which is a constant which tells you how much velocity do systems have that are far apart in the universe. The further apart things are in the universe, the faster they're moving away from each other. That is what gave us the idea that the universe, when you play that movie backwards, turn the movie backwards, turn the time backwards, when you let that all collect together again, it looked like the universe came from a little spot. So now when the explosion happened, everything expanded, and it turns out that that particular relationship between what is the velocity and the distance is something called the Hubble Constant. And it's somehow, people now think, and this is sort of for those experts here, these are the best numbers, this is a probability, and this is the best numbers people have for what the Hubble Constant is from supernova explosions by looking at great distances and trying to figure out what the distance to them are and what is the shift in the spectral lines. So you get the velocity. It's a Doppler shift again. That's one. And then there is another one, which is this one, which comes from the cosmic background radiation, which is a thing that was discovered later, and you need that to model this expansion. And here is what if you take the following idea. Yeah, here's the idea that was used to get another way of doing it, completely different, completely independent of all the other methods. And that was to use the two neutron stars. You know what their masses are from the waveform. You know the Einstein field equations. You know how strong gravity is. So you know how strong the gravitational field should be, the strain field that you measure in your detector. You know how strong that should be. You calibrate your detector. By calibrating that detector and knowing the redshift of a galaxy that's near that place, you can get another way. This is the Doppler shift. You can get another way of getting the distance, independent way of getting the distance to that pair of neutron stars, completely independent of electromagnetic methods. And those are very complicated. They're very hierarchical. And so it turns out that there's a future, which we'll get to in a second, for this field in doing cosmology with a completely different set of errors that would be very useful. You can see in this case, the two methods, the supernova method and the cosmic background method don't quite agree with each other. This is the number that you get out of them. And they are now sort of, there's a scandal about, oh, they don't even overlap in their uncertainties. Well, here is the best you can do with the one observation of the gravitational waves, but you can do much, much better as you get more and more of these. So that's a big step into the future. I don't want to go into this thing, except I'll leave it for the questions. What it is what is the possible future development of this field? I'll just tell you so you know, and you can ask me about it. Because I'm starting to try your patience. I can see that. And that is that you can make better and better detectors. We know how to do that. And this is sort of a progression where we are now. Here's where I like to be. This has now gone strain again. This is frequency. And we are not quite at sensitivity. This line is not equal to that line. So we have not yet made the design sensitivity, and we can't ask for more money. Okay? So we have to get that right. But then there are ideas floating both in Europe and also in the United States to get way down in here. A big factor of 30 or maybe even 50 in sensitivity if one actually solves these problems. And here's my last slide. This is a picture of sort of what's going on in the near future in this field. This is the last picture and the last slide I want to show you. What it is that this is frequency, and these are strains. So for example, this is 10 to the minus 25. This is 10 to the minus 5. It's a huge dynamic range. And it's also in frequency. It's an enormous dynamic range. And it's better to see it up here. This is 1 over the age of the universe. This is years. This is hours. This is 10 to the minus 1. This is a tenth to 10 hertz to 10 hertz to a kilohertz. That's the region of LIGO. And there's LIGO. And it has its sources, and you know about a good many of the sources now. Turns out there's another project entirely that's about as old as LIGO. Started about the same time, which would look at gravitational waves of periods of hours to minutes. And this is a satellite project called LISA, Laser Interferometer Space Antenna. And that thing has been studied very, very carefully. The United States was deep into this until lately because they had money problems at NASA, but they're going back into it. And the Europeans have carried it through that epoch. And what it is there are 3 satellites. You can see them. Maybe you can't, but there are 3 satellites in an equilateral triangle going around the sun in the same orbit, distance from the sun as the Earth. And what you do is you can measure their separations by laser interferometry, but of a very special kind. And that has already been tried now. In fact, there's a thing called LISA Pathfinder, which was put into this orbit, and they were able to show that they could get the interferometers running. Not between big satellites, but within the satellite. All the stuff worked. So that's a very big step forward. The hope is to have this operating sometime in the 2030s. This is a project that's actually going on right now. That's a project called Pulsar Timing, and it's done by using radio telescopes all over the world and timing pulsars. Same thing that was done when the Hulse-Taylor thing, but now these are pulsars that are moving very quickly. They're spinning at a rate such that they don't chirp. They spin at a constant rate at about 600 times a second. Imagine that. A big star, a star with mass of the sun, things spinning around like that. And it has a searchlight beam on it. And what the idea is the following. You follow if you have gravitational waves coming into our galaxy, they're coming into our galaxy. If you keep measuring these pulsars, and you notice a specific pattern, you notice that in the north, let's say the northern part of the sky, all the pulsars are going a little faster. And you look in the southern part of the sky, and they're all going a little faster. And then you look in the eastern part of the sky, they're going a little slower. And you're going in the western part of the sky, they're going a little slower. That tells you something, that a gravitational wave has passed between you and all those pulsars. And that's a way of detecting the gravitational wave. But with periods, very long periods of years, or maybe months, somewhere between there. And people have been trying to do this. It's not such a hard experiment to do. They haven't yet succeeded in measuring anything, but they're getting better and better. So the last one is this one, which is also an experiment that's going on now. And that's to measure, and I will only give it to you in the loosest way. You can ask me questions about it. This is using properties of the cosmic background radiation. That's the radiation that comes from the moment the universe was created. We see that radiation. It makes static on your radio, by the way. If you go on your FM radio and you go between stations, 10%, if it's a good FM radio, is the noise from, is the heat radiation from that explosion. You listen to that a little bit in your own house. You may not know that, but that's a worthwhile thing to know. And so now, what happens is that that radiation has certain attributes that electromagnetic radiation has, the polarization of the radiation, the same kind of thing that your Polaroid glasses, your sunglasses, can eliminate if you want to. You can rotate your sunglasses and see that there's an axis, a direction of the electric field in the light. That axis is moved into very special patterns by gravitational waves that might have been generated at the moment. I mean at the moment, 10 to the minus 30 seconds after the explosion of that made the universe. It's a fanciful idea, but there must have been tremendous accelerations and quantum fluctuations, not classical fluctuations, quantum fluctuations of the universe at that moment, and they made gravitational waves. And those gravitational waves make a specific pattern of the polarization. People have been looking for that. They thought they saw it about 3 or 4 years ago. They were mistaken. They saw what they were really seeing as dust in our own galaxy causing this. But now they have much better experiments, and the same people made the wrong announcement. They're deep into it still, and they have now gotten to the point where they've made an announcement that they don't see anything at a level that's about twice as good as what they thought, where they claimed they saw something. But that says something very important. They're onto it. They're knowing how to do the experiment right, and I hope within the next decade, they either will definitely see gravitational radiation from that epoch, because LIGO can't do it, LISA can't do it. It's the only way you're going to get that piece of information, which is an absolutely spectacular piece of information. The gravitational waves that come from the moment when the universe was made. Thank you.
I'm going to try to take a few questions. I'm going to repeat them so that everyone can hear. So I saw a hand, at least initially down here, right here. Yeah. Go ahead.
Yeah, could you do me a favor, stand up when you ask your question? Whoever's asking.
You? Yep.
Okay. Okay. No, I think I understand the question.
Okay.
Because it was complicated. Stay standing because I want to make sure I have your question. Okay. And that is that you would like to know something about the amplitude of gravitational waves from binary black hole collisions in different places than, in fact, why don't we see them in our own galaxy? That's one of the questions you asked. And I didn't really tell you where the black holes are that we saw. So that's the second part of your question. So let me try to answer that, okay? First of all, I made a terrible mistake not to tell you where the black holes are that we did see. So you can sit down if you want, or you can welcome to stand, but but the thing is that those are about 1 billion, 10 to the 9 light years away. That's how far they are. So those of you who know a little cosmology will realize that they're pretty close to us. They're at a z, that's a redshift of 0.1. They're not, the edge of the universe is at a redshift of about 1, if you want to, in order of magnitudes. So these are fairly modern devices, those things that we're looking at. They're fairly late in the evolution of the universe. Now, we see one of those every month, about, okay? That's what we see. That's all. If you put all the ones we've seen, including some you don't know about because we haven't told you about them, it's about, we get one of these guys a month. And we're looking at something that's the thousandth of the size of the universe. That's about the size. So now you go down to the size of our galaxy. You're in the 10 to the minus 7, 10 to the minus 8 size of the universe. And you don't expect to see one once a month. you might expect to see one once every 10 to the 8 years. So that's why we don't see them from our own galaxy. They're not very, I mean, seeing one a month from a volume that's 1,000th the size of the universe, that's z of 0.1, that tells you it's a pretty rare event. And you can convert that into the number of black hole pairs that live and make a decay in a given volume of the universe. I can't convert that for you. I think that you can do it from that number I just told you. And I think that will answer your question for you.
All right. How about right here?
Okay. Good. Thank you for the question. The question was, I didn't mention anything about the higher frequency end of the spectrum. And I was being very, very careful. I'll now not be so careful. Okay? It turns out that the place that LIGO is sensitive, you could see that from the spectrum I showed you. It's sensitive from about, it's most sensitive about 100 hertz. Okay? That's where that minimum is in the noise. But you could still, and more modern things you can think of and advances we can make, we think we can probably get pretty good sensitivity from 10 hertz, 10 cycles per second, 10 hertz, all the way up to about maybe 8 kilohertz. And now I haven't told you anything about what's going on at frequencies above 1 kilohertz. And it turns out there's some fascinating, interesting sources that we now know about that we should be able to detect. And one of them is the following. This is, I think, I said very little about what really is the next step in any of this stuff. But let's tell you what some next step is in neutron star detection, for example. We've detected one neutron star pair. It happened to be very close to us, which was, good. If we improve the detector a little bit, or if we're lucky again, and it's luck, I mean, we get an event like that maybe once a year. From now, a neutron star binary once a year. But if we now improve the detector a little bit at high frequencies, not by much more, maybe just to get the design sensitivity, we might see some spectacular thing that has to do with the following. It's called, with the physics that comes out of it, is the equation of state of nuclear matter. In other words, the stiffness of nuclear matter, how stiff it is, how much pressure you need to make a change in the density. Okay? That's the equation of state, and that's known by nuclear physicists and in very much lower densities. Okay? So it's a number that everybody would love to know. And we have some things we're going to get from the neutron star binaries, and one of them we're going to see is that as the neutron stars get close together in their orbit, they start making tidal distortions. They pull each other apart. The gravitational interaction is making the neutron stars look a little oblate with axes that are along the axis where they are closest. And so we're going to see how stiff they are from that, and that we can get from the exact motion. So that's one way we'll get an idea of the equation of state. And that's all within the band that we're now familiar with. But there's a very interesting effect predicted for much higher frequencies, from about, we don't know where, 800 hertz all the way up to maybe 3 kilohertz. And what that is when the neutron stars have collided before they make a black hole, a lot of people think in their modeling that we're going to get some sort of collective body motion of all that cloud of neutrons that are bending of them and longitudinal excitations of them, oscillations of that cloud of neutrons. And those will tell you how stiff the neutrons, they'll give you the Young's modulus, effectively, of the nuclear material. And those have frequencies all between 800 hertz up to about 2 or 3 kilohertz, depending on the equation of state that nuclear matter has. And we have a chance, with even the detectors we have now, at those high frequencies to see these, because they have a fairly long-lived state. They have many, many oscillation periods. They almost look like quasi-periodic sources. So that's not an answer to you, but that's the thing that's in the future. What our real future is really in making the detector sensitive all over, at high frequencies and low frequencies more, and getting into cosmology. In other words, that's why I made a little fuss about the Hubble Constant measurement you can do. Turns out you can use these black holes, the black hole collisions, or black hole with a neutron star. That's another thing that must exist. That would be a very elegant system, for example, for doing a lot of the measurements that have been made of the cartography of the universe, And that gets you the equation of state for what's called the dark energy. That would be very useful, and by a completely different method than the way that astronomers now do it. By using gravitational radiation and using the Einstein equations, and using that much like we did to get the Hubble constant, now from this one simple system. And that allows you then to make a completely different survey of the universe using not electromagnetic radiation, but gravitational radiation, which will have its own problems, but different problems than the electromagnetic case. And that's something we're looking forward to. That's going to take an investment on all our parts if we want to have that. It costs money to do that.
Yeah. All right, how about straight back here? Yep, the person who just looked behind him. Yep, you.
Stand up, I can't see where you are.
You're right there.
Where are you? Oh, there you are, okay. Yeah, okay, I got you.
What is the laser wavelength? Specifically, going to shorter wavelengths or longer wavelengths?
Good. So good, you asked a nice technical question. What he asked is, I think you really asked, why did we choose 1 micron? Because I didn't tell you that. Why did we choose 1 micron as the wavelength we use? And that's a somewhat unfortunate choice. Why? You can't see it. I mean, we started with green, which you can see pretty well. But it turns out that the lasers that made green in those days when we started were very, very inefficient. You know, I don't know how much laser physics you know, but we started with using the argon laser, which has an efficiency of, for 1 watt of light out, you have to put 10,000 watts of power into it. Okay? It's crappy. I mean, it's a lousy thing. You go broke paying the electric bill. So it turns out that the most efficient lasers we have, which are about 10% efficient, these are solid-state lasers, which their base frequency is, they're called neodymium YAG crystals, and you can make neodymium YAG glass. You can do all sorts of doping of glass. They are a very popular material, not so hard to grow, and they make beautiful lasers, but they happen to be, unfortunately, at 1 micron, 1.06 microns. Now, if you want green, you can frequency double that, and we are now doing that. Okay? But it's a mistake. It turns out there are all sorts of good reasons, which we found out in the end, why 1 micron is a lot better than half a micron, which is what the green light is. Why? Because it turns out the mirrors can be made better. The coatings can be made better. So all the advantage you might get out of the fact that you have a factor of 2 smaller wavelength is destroyed by the fact that the technology is not able to keep up with the better optics you can get at 1 micron. So you can see that's the logic behind the 1 micron. And right now, that's enough. You don't want to hear more.
Okay, I think we can do one more question. Okay, right down here.
Oh, wow. First of all, let me say something about Joe. I knew him pretty well, and at the end of his life, he was doing something zany. And I have often wondered, but he was also, let me say, but he was actually seeing scattering of neutrinos by salt crystals, and he was arguing that an organized salt crystal, a nice made thing, salt, made as a crystal, was a better scatterer of neutrinos than just random amorphous salt. And it turns out that he had got everybody in the United States Navy scared to death that he could make a device that he could give the Russians that would allow them to find our submarines, because they had reactors in them, and they make neutrinos. Okay? So that's how he got himself into trouble at the end of his life. He got into trouble over and over again. But he did some absolutely spectacular science. In the beginning, he was one of the co-inventors, but he's not given credit for it, of the maser and the laser. He was a microwave spectroscopist. That's what his background was. And he got interested in gravity as a side issue. But he was one of the people who decided you could make negative temperatures. You could make, for those specialists here, you could invert a population so that they're more in an excited state than in a ground state. And he wrote a paper about that, but where did he put it? He put it in the Journal of Electrical Engineering. Nobody paid attention to it. So, now you ask me, what do I think he saw? I never was able to get him to agree, okay, but I'll tell you what it was that I thought it was. And that doesn't mean it's true. I thought it was magnetic pulses. I had a student, one of my undergraduates, we always give projects to undergraduates, just the same way you do. And one of the nice projects was, we made some big coils. And we took one of the coils and took it to Argon Lab and put it next to unbeknownst to him, we put it next to his detector at Argonne Lab. And I had one in my house, and then we had one at my lab. I live 8 miles from MIT, so we had 3 detectors. And we saw millisecond pulses of milli-Gauss fields. And you see about 3 or 4 of them a day. And those are thunderstorms in the country. And that's what I thought that's what he was seeing, because he probably didn't have enough magnetic shielding. That was my guess. When I mentioned that to him, he looked to me like he was so mad with me that, you think I would make a simple error like that? What do you think, I'm a jerk? Okay? And so I never pursued it. Okay, that's the best answer I can give you. It's not a good answer.
All right, so before we break up, I want to just present you with one last thing. We have a plaque that is honoring the 56th annual Alphaeus Smith Lecture. And your name is now on the plaque, along with the other 55 lecturers. So when you have a free moment, you can sort of peruse the names on here and see what good company you've kept.
Wow.
So.
Well, I'm sure they're all a hell of a lot better than I was. Okay. Wow. I'm looking at the list. This is a joke. You had Phil Morrison talking here.
Absolutely.
Well, Phil Morrison, bless his soul, he's dead, was the guy who almost killed LIGO at MIT. Why? Because he didn't believe in black holes. What did he talk about here? There he is, right there.
Well, that was 1968. I wasn't here yet.
Oh, you weren't here yet, okay.
So.
Thank you very much for this.
Thank you very much for coming.
Thank you.